Okay, good morning. 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 Okay. So, any questions before we get started? So this week we did a bit of a revision of row reduction kind of stuff, all the rank, column spaces, row spaces, all that kind of business. Inverses of matrices. We really worried about AB equals BA equals I, whether you need one or both, and you only need one of those things. And then we talked about the rank nullity theorem, which has various consequences. And one of the key takeaways from that is if you have a linear transformation between two finite dimensional spaces of the same dimension, then it'll be injective if and only if it's surjective, and therefore if and only if bijective, an isomorphism. All right. So for the practice class today, as always, we have lots of examples of things. The first one here is, so we've got some matrices and we need to find everything, basically. And we need to find bases of the column space, which will then tell you the rank. Remember, the rank's just the dimension of the column space, so once you found a basis, that tells you the rank. A basis of the row space, and the determinant. That's a bit of revision from, we'll be talking about determinant again in the following week. And then the inverse, if it's invertible. And everything comes down to just finding, as we should know, this is one of the bread and butter things in linear algebra, just finding the reduced row echelon form of the matrix. Well, actually a row echelon form will do, but we'll go all the way to the reduced row echelon form, from which it's easy to see which columns of the matrix form a basis of the column space, and also which rows form a basis for the row space. All right, so let's just churn through one of these. The first example, I'll move it down here though, so F. So the first example, A, let's call it. I like working over F2, that's very easy to do. So we reduce it down. I'll bring the fourth row up to the second row place. Maybe I shouldn't have done that yet. Well, yeah, I think I should. Well, let's do one thing at a time. So subtracting off or adding the first row to the second row, as you like. And now I'd better swap the second and third rows. Yep. Have I done it all correctly so far? Oops, I think I copied something down wrong. I put a 0 here when there should have been a 1. And at the same time, well, I'll kill off that row using the second row. We're not completely done yet. We have to kill off all the stuff above leading ones. So that's this and, well, that. So I'll use a multiple of row 3 to kill off that 1 in row 2. And that'll do it for us. So okay, so that's the row reduction. So that's the reduced row echelon form. bit big there, but anyway, there it is. I guess I can scale it actually. Somehow. How do I make it smaller? Oh, there we go. Good. And then from that we know everything because, so I'll just emphasise again, so you're probably quite bored of it by now because I've said it lots of times. So we look at the columns which have leading ones, so that's the these ones. Oops, what am I doing? Just looking for my highlighter. There we are. So columns with leading ones, this one, and this one. And the corresponding columns back in the original matrix form a basis for our column space. This one, and this one. Let me know if I've made any mistakes. Okay, so it's those three anyway. So basis for the column space is 1, 0, 0, oh sorry. 1, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 1, 1. Now, basis of the row space, here, so remember there's two subtly different things happening. When you're doing row operations, you are changing the column space each step, but the column space is isomorphic as you move along. And that's why we have to look at the columns here, but then go back to the columns of the original matrix. But in terms of the row space is the space spanned by these 4 rows of that matrix is the same, exactly the same as the space spanned by the 4 rows of that, same as that, same as that, same as that. Okay? Because row operations clearly don't change the span of the rows. So here we have to grab the, it's clear from the reduced row echelon form which rows form a basis of the row space. So it's the row, it's in this case it's just the rows that have leading ones. Okay? Which would just be the non-zero rows, in fact. I mean, it's all the rows, everything below that, the ones without leading ones, are just the 0 rows. So those 3 rows form, but we'll transpose them because we normally consider the row space not as row vectors, but turned around to become column vectors to fit with our usual convention of having vectors being columns. So it's those 3 vectors there, which I can just fit on there. So it's 1, 0, 1, 0. That's the first row transposed. And then 0, 1, 0, 0. And then 0, 0, 0, 1. Notice that you, well, maybe you can in this example, I'm not sure, but you can't take the corresponding rows of the original matrix and expect them to form a basis. Because, for example, you've done row operations that swap rows around, so you've like screwed around with things. Maybe in this example you could have, I don't know, but that would be a coincidence. Okay. Make sense? All right. So as I said a few times, that's like bread and butter thing to do. So the rank is then just the dimension of the column space by definition, so that's 3. Yeah, rank, there we are. I was doing that one. The determinant we can quickly compute. Let's do that. Yeah, so we could, indeed, we could do it just from the row echelon form here. We've got a row of zeros, so we've got determinant 0. So remember, but we'll discuss that again next week, but you remember it. It's again a bit of, there's this weird like bit of revision and bit of doing things more formally in this course. But remember, when you're doing row operations, you do change the determinant, but you only change it in very predictable ways. So if you swap 2 rows, you multiply the determinant by -1. If you add a multiple of one row to another, that does nothing to the determinant, leaves it unchanged. And if you multiply a row by a number, it multiplies the determinant by that number. Okay, so doing those calculations, if your reduced row echelon form has a 0, 0, 0, zeros, your actual determinant is just some scalar, non-zero scalar, which might be plus or minus 1 or whatever. So non-zero scalar times the determinant of the reduced row echelon form. So if that guy is 0, then that guy is 0. Okay, that would be one way of seeing that. However, let's just compute the determinant by hand. So it's 1 times the determinant. I'm just going to expand along the first row. Minus 0 times the determinant of crossing off the row and column of 0. So hopefully this is very familiar. If not, you know what to revise before next week. I think I'm doing it right. Plus 1 times the determinant of, I mean, I put the 0 there. It's stupid, of course, but I'm doing it so you see remember the pattern. And then minus 0 times the determinant. Of course, I wouldn't be writing out all these 0 things. Well, I'll never do it. I'll never do it again. Okay, so that first one is 1 to, well, 1, I'll get rid of the 1. So it's 0 minus 0. So 1 times the determinant of this guy, 1, 1, 1, 0. Plus, then I'll expand out this determinant, 1, 1, 0, 1. And that's 1 plus 1, which is indeed 0, as we knew, because our reduced row echelon form had a row of zeros. Okay. Good. Another way to explain that also a matrix is invertible if and only if its determinant's non-zero, and it's invertible if and only if its reduced row echelon form is the identity. Its reduced row echelon form isn't the identity, so it's not invertible, so it's got 0 determinant. I mean, you can go around in circles with various ways of thinking of things. Well, not circles, but lots of different ways to get to the same conclusion. Good, so I think we'll leave that question because that's all pretty straightforward. Oh, and it says find the inverse if you can. Well, this is not invertible, so we can't find its inverse. You remember how to find the inverse? We discussed that. Matrix A, the identity, do the row reduction, get the identity there, whatever spits out over this side is the inverse. Yeah? If it's a non-square. Yep, if it's a non-square, is that what you said? Yeah, non-square. Yeah, exactly. If it's not a square matrix, inverse doesn't make sense. Yeah. And you can sort of see why, I mean, thinking of things of linear transformations, we can sort of work, well, you can also see why just because putting an A, a B on that side and a B on that side, making it equal the identity, your B is going to have, like, the rows and columns are going to be all screwed up, the number of rows and columns. But let's think just in terms of linear transformations. If I have something that's a non-square matrix, so let's say it has fewer rows than columns, that will mean its domain as a linear transformation is higher dimensional than its codomain. Its domain is the number of columns that it has. That's, because when you multiply first the length of the row, how many things are in the row, which is the number of columns, times that vector. That's how you do matrix multiplication. So its domain is the number of columns, dimensional, and its codomain is the number of rows, dimensional. And so for that to be an invertible map, it needs to be an isomorphism between those two things. But, two vector spaces are isomorphic means their dimensions have to be the same, finite dimensional things. Okay. So number of rows has to equal number of columns. All right, great. Okay, so that's something that question you know how to do in your sleep now is the point. This one's a bit, is this the one? Yep, this one's a little bit nicer in a way, or we have to think a bit more. So now we're taking subspaces just of our favourite vector space, Fn. And we're trying to find and we're given a subspace, and we're trying to find a complementary subspace. And then remember that there's a whole heap of ways of finding complementary subspaces. it's highly non-unique thing. There's lots and lots. You remember we were talking about in R2, if you've got that subspace, then any subspace that's like this is going to be complementary. So there'd be infinitely many. So we want to try to find one though, and we want to try to think of a nice-ish way of doing it. So in particular, like to make y nice. So for example, I'm adding let's say that we want to make y a subset of the this basis of y being a subset of the standard basis vectors for Fn. Or another way too. But anyway, so it's a question for you. How should we find a complementary subspace? Maybe the thing that makes it hard in some ways is that it's highly non-unique. When there's only one choice for something, it's normally super easy how to calculate it. There's probably basically a formula, multiply this by this, and that's the answer or something like that. But when there's lots and lots of options, while in principle it should be easier, but in practice somehow the choices you have to make can be confusing. So what should we do? Good. So as a starting point, we can start with, let's actually start with a basis of Fn. And then, but we want to, so the hint that, so it's sort of what you were saying, but the hint now is that we want to modify that basis. So let's just take the standard basis of Fn. So we won't make life hard for ourselves. So just take the standard basis of Fn. But that's not really but then what we want to do, we want to ultimately have a basis of Fn which looks the following. It's meant to have the basis of X here first, and then the rest is meant to be what makes up the complementary space. So now we're in the game now of taking one basis and modifying it to try to throw out some vectors and throw in some other vectors. And that should be a hint of what thing we did that tells us exactly how to do that. It's possible, but there's something easier. I have something easier in mind that's going to be less sort of calculation somehow even. And it was something early on when we were talking about basis and dimension, before we even knew that dimension made sense, that every basis had the same number of elements, there was a key lemma that we used, and it was called, I think so, the replacement lemma. Might be the only lemma we've done, so that'd be good. So it's a replacement lemma. So let's think of how that works now. So we just take our favourite basis of Fn, the standard basis, indeed, and now we want to, well, we look at these guys. We write this in terms of the standard basis. Well, that's easy. It's 2 times E2 plus 2 times E3 plus 1 times E, etc. And then as long as a coefficient of, remember how the replacement lemma worked, as long as it's got a non-zero coefficient, for example here in the E2, then I can throw away E2 from my basis and throw in this instead. Okay, and I get the same, it's still a basis. That's what the replacement lemma said. And then do it again. So then we have a new basis consisting of this, along with E1, E3, E4, and E5. So now I do have to do a calculation. Now I have to write this guy in terms of that basis. So the basis that consists of the first guy here plus the remaining e's that I haven't thrown away yet. And then just look for, I don't want to throw away this guy, so I won't throw away this guy, but I'll look for one of the other e's for which there's a non-zero coefficient, and I'll throw that one away and put this one in instead. And that'll work. That'll always work because we're told here these are linearly independent sets. Somehow, if these weren't linearly independent, you'll get to the point where you have to throw away one of the guys you already had, because they're the only ones that, like when I write this guy in terms of this other basis, maybe it's just a multiple of this, and then I'm only allowed to throw away this guy. So you'd sort of see it in the calculation. But that's not going to happen to us. All right, so we're going to use replacement lemma. So start with favourite basis of Fn, and step by step convert into a basis of the form. So let's call these x's, let's go v, vi, such that I is whatever it was. Let's say that was our basis of x. Union some ej's such that j is everything but not in I. So our indexing set is 1 up to n. Let's say, I don't know, it's getting a bit convoluted, but 1 up to n but not I. It'll be some subset of the right size that makes up the dimension. And then this will now be our basis for y. And notice it's a little bit, until you've thought through that process that we just discussed, it's not that clear that you should always be able to pick the a basis for the, you could pick a complementary subspace which is spanned by just, in this very nice way. I mean, these are nice subspaces, these ones, that are just spanned by a subset of the elementary basis vectors. But that's what this process shows us that we can do. Okay, so it's sort of surprising. You can pick such a nice basis. So how does it work? So first, let's call these V1 and V2, or X1 and X2, but let's say V's. So the first step is V1 equals 0 E1 plus 2 E2 plus 2 E3 plus E4 plus E5. And I can throw away any of those that have a non-zero coefficient. So the only one I can't do is I can't throw away E1. That's what it's saying. So if I tried to throw away E1 and put V1 in instead, it won't be a basis, is what's happening. And that's, and you can, of course, you can see that. If I threw away E1 from my basis and tried to toss this in, everything in the basis is going to have a 0 in the first component, which is, of course, yeah, you can't span everything then. Anyway, but so V1, comma, E1, E3, so I'm just making a choice here. I'll throw away that. Is a basis of V, of the whole space. And now what I have to do is take V2 in this basis, this new basis, and it should be pretty easy to write V2 in this basis. So have I got V2 frozen over there? No, I'll make sure I do. I mean, if we have to, we can resort to equations to find it, but maybe we can just do it by looking at it. I mean, because we haven't got any E2s in here, the second component tells us exactly what it has to be. So V2 has to be 1 times V1, because it's got the same 2 in there, and then the rest is just what it has to be. So V2, by looking at the second component, I know that it has to equal V1 plus, and I just have to, what do I have to do to V1 to make it all work? I'm using just E1, E3, E4 and E5. So using E1, I have to add subtract 2 E1s. Sorry, I can't see that screen over there, so I'll look at this one. So V1, yeah, I have to add 2 E1 I don't do anything with the E3s or E4s or E5s, in fact. So now the point is, whatever I need to pick one of those non-zero coefficients, toss that guy out and put the V2 in instead. And there's only one choice now because I don't want to throw away V1, of course, that's what I'm trying to keep. So I throw away E1. So these guys span X. And Y is going to be defined to be the span of these guys. Okay, good. So that, I mean, it's a method that you can, it's a good, like, little game with the replacement lemma. You have to make little calculations as you go, write vectors in terms of new bases, but they're pretty easy calculations, it turns out, because our initial basis was standard vectors. There's still choice, of course. There's which coefficient you throw away. But anyway, it's still fairly straightforward. There's like millions of different ways you could try to find a complementary subspace. So certainly use your imagination to come up with other ones. But I do think this is kind of the most, let's say, enjoyable way to do it. Make sense? So maybe we could look at one more quickly. Let's do this one. All right, I'll freeze that. Okay, so this one was in F5, 6. Okay, same thing. We start with E1 up to E6. Then call our vectors V1, V2, V3. V1 equals 2E1 plus da-da-da-da-da. So let's throw away E1. So now our new basis is V1, E2, E3, E4, E5, E6. Now we have to write V2 in terms of that basis. But again, here's the thing, it's easy to see. V2 is some multiple of V1 in that first coordinate. So 3. It's 3V1 plus some stuff. And what's that stuff? So now 3 times that's 6, that's 1. So 0 E2s, I think. 3 3s are not 4. So plus 2, I think. 4 plus 3. Right, so here my arithmetic's going to fall apart. 3 2 is 6, which is 1. So I think I have to add 2. 6, which is 1, plus 3. and that one is going to be 0, 3 layers at 1, so plus 4, E6. Something like that. Doesn't matter that much. Well, unless I'm saying something non-zero, which is 0, then I'll be in trouble. But assuming I haven't done that, let's toss out that one. So say that again. First component of V2 is 1, which is 1 though, because we're in F5. Yeah. So we're working in F5. So I think, roughly speaking, I've got it right. So we have to keep E2. Well, I'll write E2 later. V2. We've had to keep E2. We've thrown away E3. We've got E4, E5, E6. Final step, V3 written in that basis. And now it's the things that are missing that so now I have to do a little bit, I guess. V1 and V2. At a certain point, maybe I should just write some equations and work it out, because I'm going to get too confused. Well, okay, let's assume I have to use equations. Because at a certain point, it just gets hard to guess things. But it'll still be really simple equations. Because that says 1, 0, 2, 1, 2, 3 equals, so lambda V1, that's 2 lambda 1 plus lambda 2. And then I haven't got any E1s left, so that's the end of that. The E2 component, I've got 2 lambda 1 plus lambda 2 again. And then I have still got a lambda 3 for the E2, because that comes from this guy. There he is. Now, the 3, I get 3 lambda 1 plus 2 lambda 2, and nothing else, because E3 has been tossed out. So what I'm working out when I do this, I guess I'm seeing that I should just use those two to find lambda 1 and lambda 2, and then everything else will be easy. But anyway, let's go through it in gory detail. So then 1, 2, 3, fourth row, I think now, 3, which is 2. 2 lambda 1 plus 3 lambda 2 plus lambda 4. Fifth is 2 lambda 1 plus 4 lambda 2 plus lambda 5. And the sixth is 3 lambda 1 plus 0 lambda 2 plus lambda 6. So I do get lots of equations. Let's just work out lambda 1 and lambda 2. So using just these two rows here. Anyway, maybe you've already done it in your heads, but using those two rows, we get the equation 2, 1, 3, 2, 1, 2, which we reduce down. I'll make this a 1 first by multiplying by 3. And then I'll just subtract off, indeed, 3 times that row. 2 minus, or maybe I should just add, sorry, I'm going to add the previous row, that's even better. 3, 3, which then becomes 1, 1. So now I think I'm in business. So now I know that lambda 2 equals 1 and lambda 1 equals 3 minus 3, which is 0. Is that really right? Lambda 2 is just 1. Oh yeah, I could have seen that in my head. So now I'm probably I've done something really slow here. So then we work out everything else. Lambda 3 equals 2 minus 2 lambda 1, which is 0. Lambda 4 equals, so I'm just looking, that one matches up with the 1 there. So that's 1 minus 2, so minus 1, which is 4. Lambda 5 is 0. And lambda 6 is 0. So I should have been able to see that quicker. Sorry. Anyway, good. So V3 equals V1 plus 0 V2 plus 0 E2 plus 4 E4 plus 0 E5 plus 0 E6. So hopefully that's right. Anyway, I'm not going to do it again if it's not. The point is, we've still got at least one non-zero coefficient. That'll happen if the original set was linearly independent. But here we actually haven't got a choice. We just have to toss away E4 and replace it by V3. So our basis now is V1, V2, V3, union, E2, E5, and E6. Good. Anyway, sorry, that one took a bit longer than I thought. Any questions about that? All right, replacement lemma is great, is the philosophy there. In this last one, we're doing some matrix representations, but here we're not given exotic vector spaces, we're just given Fn and Fms, and our linear transformation is given by a matrix. So already we've got a matrix representation, but that's with respect to the standard bases of the domain and the codomain. So in this question we're asked now to take a more exotic basis, let's say, I don't know, let's do this one or something, a more exotic basis of the domain, and, well, that's just the standard basis of the codomain. Maybe we should pick something. Are they all one or the other? Let's do this one all the way down here. So we've got these two different bases of codomain and domain and codomain. Okay, so let's do indeed this one that I just said. This one. F2 is also fun to work with, so we'll continue with that. So remember what we've got to do. We'll call, this is our basis B of the domain. And we'll call that, B1, B2 or something. And this is our basis of the codomain. A, A1, A2. And remember what we have to do. We have to compute theta of B1. So in this case, I'll just write it out in sort of gory detail. If this was alpha B1, sorry, not B1, this is in the codomain now, so A1 plus beta A2, and theta of B2 equals gamma, say, A1 plus delta A2, then the matrix representation of theta with respect to these bases, and we put the indices like this, the basis of the codomain is the one we write first, and then the domain, is just these alphas and betas give the columns. First column is that, second column is that. Okay? So remember they're columns. Oops, meant to do that in a highlighter. Column, column, row, row, those things give us columns. So we just have to do the calculation. So theta of B1 in the first example is, well, we've got an explicit matrix. Oh, it's the identity, but that's okay. There's always something too simple in all of these questions, but it's fine to be so we're going to find the matrix representation of the identity with respect to these two different bases, and it's not going to be the identity anymore because the bases in the two different domain and codomain aren't the same anymore. If you take the same basis in domain and codomain, the identity will always have the same, will always be the identity matrix. But now it'll be something different. Anyway, let's work it out. 1, 1. That equals 1, 1. I mean, I didn't really have to do that matrix multiplication. And I can write that in terms of the code, in terms of this basis, this 0A1 plus 1A2. So it's nice and simple. Of course, as the examples get more complicated, the process of writing your vector here as a linear combination of these, you might have to write out equations and solve equations to find the coefficients. But here we don't really have to. This time it's of course 1, 0 again, and well, that happens to be A1 plus 0 A2. It's a bit of luck. I mean, it's picked so easily, this example. Yeah?
What does that matrix tell us?
Which matrix?
Like the alpha, beta.
Oh, this matrix is telling us that if we, because, you know, there's nothing special about the basis, the standard, I mean, there is something special about the standard basis of Fn, but it's not like the, you know, there may be other reasons why you want to look at other bases. And similarly for the codomain, I mean, you don't want to always fixate with the standard basis. You might have some other, in a particular problem you're looking at, there might be another basis that you're interested in vectors like this instead, so certain particular vectors spanning a parallelogram or something, and you want to write everything in terms of those. Okay? So what this matrix tells you is that if you imagine this first basis vector, well, you now make an isomorphism from F2 to a new copy of F2, where this guy plays the role of the first standard basis and this guy plays the role of the second standard basis. And then similarly in the codomain, this matrix is telling you how to perform the linear map theta using just matrix multiplication, where that first standard basis vector is imagined, let's say, to be the first basis vector and this one the second. Maybe I'll finish the calculation and show you what I mean. So this equals, so theta AB equals 0, 1, 1, 0. But now let me explain what that means. So note, theta AB of 1, 0, so that's the point, like doing this with the standard basis vector gives you, so what does it give you? Let's do it. That by that plus that by that. That by that plus that by that. Which is, so this is the, corresponds to B1, and this one corresponds to A, not A1, but to A2, which is not really A2, it's this guy here. So what it's saying is if you take, or generally, if you take a linear, let me say it another way. If you take a linear combination of these two vectors up here, if you take a linear combination of these two, lambda times this plus mu times this, yeah, I'll write it yet another way. It'll be clearer this time. If our vector v is lambda times b1 plus mu times b2, then, and theta of v equals some other coefficients. So what's it going to be? Nu and eta or something. A1 plus eta A2. What the matrix representation is telling you is that theta, it's telling you how to find these nus and etas without having to go and perform the linear operator, but instead just do matrix multiplication. So what it's saying is to just do theta AB of the vector lambda mu, and that's what I mean when I say we sort of pretend or something. When you're doing the calculations with the matrix representation, this guy now become, for the purpose of that matrix, the matrix representation, this guy is the first standard basis vector now. And this guy's the second standard basis vector. That's what I mean here. Coefficient of the first standard basis vector, coefficient of the second standard basis vector. And it spits out, by matrix multiplication, the coefficients here and here. The coefficient of, so in the codomain, these guys now play the role of the first basis vector, second basis vector. Okay? And somehow it's a bit confusing in this example because the original theta was given as a matrix already. But it's somehow better to imagine examples like we did in class where the original vector space wasn't just Fn, it was polynomials of degree something, whatever. Yeah, some more exotic vector space. And then you want to take, you're doing theta of some linear combination of a choice of basis of the domain, and you're wanting to write it out as a linear combination of some choice of basis of the codomain, and the matrix representation turns that into a matrix calculation, just doing exactly what I said here. Is that sort of clear? Clearer? Slightly clearer? Anyway, that's the point of matrix representations. It converts doing computations of linear transformations to the incredibly concrete world of matrix multiplication that a computer could do, or whatever. All right. Yeah, any questions? All right, good. Let's finish there because all these examples are pretty much the same. So you can do a few more as practice. Good. Okay. See you next week.
You don't need inverse, you still do exactly the same thing. You've got this choice of basis of the domain, you have to do this matrix multiplication onto this vector and write it. No, you don't want to get rid of one. Your matrix, it doesn't matter about invertibility or injectivity or anything yet. It should still be a two-way. You want to apply theta to each of your basis vectors. Write those as linear combinations of same size. That'll give you three equations. So coefficients that you've got, that plus that comes first column, second column. Oh, okay, yeah, so how did you go? That's right, yeah, it'll be fine. That's good.
How do you calculate those again? Like, how do you find the theta matrix again?
Yep, so you've got your basis of the domain and your basis of the codomain.
Okay.
So you apply theta to each element of your domain and write that as a linear combination of the basis in the codomain. And each of those gives you a column.
I thought that's what you're trying to solve for using that matrix. Okay, so you need to solve that first to get the matrix.
Exactly.
Then you use the matrix to solve.
Yeah, so you do the calculation once for the matrix to write each basis vector in terms of things, and then that matrix does it for all vectors in the space now. So it's like it's the minimal amount of sort of calculation you need to do. You need to do it on a basis, and then that matrix now works for all arbitrary vectors now. It's those, as I discussed. So yeah, but you have to. There's no magic. I mean, you have to calculate them.
Why the domain can't be written in terms of the codomain?
Well, often the domain and the codomain would generally, like if it wasn't a square matrix, I think there's another class coming into it. If it wasn't a square matrix, then spaces. Two-dimensional spaces.
Oh, don't do that.
Second row.